Hello everyone. In this video, we are going to talk about another method for numerical solution of inverse kinematics problems, and that is called forward and backward reaching inverse kinematics, or FABRIK, which is an interesting heuristic method. And let me explain that again through an example to you. So here again, assume that we have the 3 degree of freedom planar arm, which is pinned down at point P1. Okay, so here at P1 you have a pin. It is not supposed to move from that pin ideally, right? That's a rigid pin. This is my initial configuration of the robot with some initial angles, and now I ask the robot to go to this point T, the target point. Well, this is the way we go about it. So we go first in a forward manner and then backward. What does that mean? In the forward stage, this is what we do. First, we try to put the end effector, which is here at point P4. We try to move the end effector at P4. We try to move it and put it right at the target, as if we could get it solved in just one single step. Right? So we put P4 right at the target. So P4 now comes to this new point called P4 prime, which is the same as the target. Good. Now what happens here is, if point P3 does not move, then the length of this member, which here we show be D3, it has to be longer. It has to be now this much. And this cannot happen because we here assume that this member is a rigid member, and this joint is a rotary joint, not a prismatic joint. We already rotated it, right? And so this member now has to change its angle from the line connecting P3 to P4 to now P3 to P4 prime. So we rotated the angle, but clearly we cannot stretch the angle, the member. So if I want to keep the member to be the same size as what it used to be, this is what I do. I connect this point P4 prime, the new location of the endpoint P4, which is again the same as target. I connect it to the other end P3, and then along this line, I separate a distance from P4 prime. I separate a distance the same as what? The same as the original length of the member. And that gives me point P3 prime, which is where point P3 should be if I do not want the member from 3 to 4 to be stretched. Good? So it's like I have transformed this member from here, now it is here. And if you look at this step, you see it's very similar to the CCD. In CCD, we did the same thing. We focused on joint 3, because that's where the last rotation was. We focused on the last joint. We connected the target to that point, and we tried to align the line going from joint 3 to the end effector to what? With the line that goes from joint 3 to the target. So that's exactly what we did. Last time we also aligned. But what's the difference between here and CCD is in CCD, we did not move point P3. We kept it in the same location, and therefore we could never reach the target point. We could come here. Instead of separating the distance from the end, we separated the distance from the beginning because we assume it cannot move. And so we end up here, if you remember, in CCD. So my member was this guy here in blue instead of this guy here in red, right? In CCD, again, the joint was immobile. The endpoints could move. Here, we fixed the endpoint to the target and we moved the first point. Okay, so that's the difference. And now, what does this one need? Well, fine. My P3 should come to P3 prime. Good, fine. Now what? Now, if P3 prime is here, again, if you look at the distance between P3 prime to P2, this length, that is bigger than this D2, right? So it means, again, now the second member has to be stretched, which cannot happen because we only can rotate it. So what we do, we rotate it, we align the lines. So now the new coordinate, the new location, not the coordinate, the new location for P2 has to be along this line, which connects P3 prime to P2. But again, since the length of the member cannot be stretched from P3 prime, I pick a distance of D2, L2 equal D2 from P3 prime, and that gives me the new location of P2 prime, and then I go and connect P2 prime to P1. Clearly, again, if you look, P1 to P2 is shorter than P1 to P2 prime. So what I do is, again, connect P2 prime to P1, then what? Then separate on this a distance of D1, and that brings me to point P1 prime. So now if you look, my robot can reach the target point, but something is violated. What? The pinpoint. The pinpoint that was on P1 and it was supposed to be fixed, point P1, is now shifted to point P1 prime. So the base support of the robot has moved, and it cannot happen. This cannot happen. This is violating our physical constraint. So this stage, which we call the forward stage, gets my end effector to the target, but it makes my ground support to mess up. So we need to fix that in what we call a backward stage. In this backward stage, we try to put the pin back. So we start with what we got from step number D here, that's what it is, and say, well, I shifted my P prime from wherever it was to this location. But that cannot happen. So let me go and put it back. How? So I connect my P2 prime to point P. This P1 double prime is the same as original P1. It's the same as the pinpoint. Let's go put it back. But again, since this member with length D1 cannot be stretched, so I connect my P2 prime to this new point P1 double prime, which happens to be the same as P1. I connect them, and again, on this line, I'm going to choose this distance, correct? The same as what? The same as actual physical distance. And that means move the point P2 prime, which was here, to now this new point P2 double prime. And again, that causes the next member to be stretched, which cannot happen. So now what? Now I will connect my point P2 double prime to the P3 prime, which is here, connected, and then on that line, I pick this distance equal to D2. That brings me down to P3 double prime. I connect my P3 double prime to the location of P4 prime, which is here in this red location. Again, separate the distance here equal to L3 equal to D3, and that brings me to point P4 double prime, which is close to the target, but not exactly now at the target. But I could put the pin back. Okay, so in the forward stage, it means what? It means put the end effector at the target. Or let me type it. It's going to be cleaner than write it here. So in the forward stage, putting the end effector at the target and modifying the locations of the joints accordingly by keeping the length of members constant. Okay, this is what you can describe as the forward stage. Right, and then you have the backward stage, which is putting the base point back to where it was and modifying the locations of joints again accordingly by keeping the length of the member constant. So in the backward stage, your end effector is not going to end up at the target point at the very end of it. It's going to be close, but at least you have not violated any what? Any physical constraint. So with one step going through forward and then backward stage, you can go from being off to what? To being very, very close. And if you repeat this forward and backward stage a couple of more times, you should be able to what? To get the target and the end effector to coincide. Okay, so one cycle of this algorithm means going through one forward and one backward stage. So clearly one cycle of that is taking a lot more computations. Clearly you see the method does not need any calculation of a derivative, slope, a divergence, anything like that, a Jacobian, and it's not super susceptible to the initial guess, just like CCD. But of course, again, it needs computations. So first, let me show you a demo, right? I am going to show you a demo here. Okay. I got some error for some reason. So well, that is quite weird. File, save as, downloads, one, here. Okay, so here I click at some point like this, and boom, you see it can get there very fast actually. And you see the error is only 0.04%. It gets you the solution. It only get it 3 iterations because your target and initial solution were very close. You can see here clearly up to 2 decimals, which is 0.1 of a mil. I have accuracy. Let me do it one more time and try to change my location to somewhere else, maybe here. And you see, it's just a few iterations. That's good enough to see 3 iterations. You see, it's way faster. And I guess my tolerance was the same as the CCD method. Let me check that. Tolerance. Yes, that's the same tolerance. But you see, this method outperforms the CCD. It's way faster. Look. There we go. Right? Done. With a tight tolerance, easily, 4 iterations. Of course, each iteration takes a bunch of computations, but not too much more than CCD, really. You see, in terms of time, it is way faster and it is not super susceptible to that tolerance, really. Now, I might wonder if I change this to -3, can it still reach? Right? So let's give it some tighter tolerance here. See if it can do it. Seems like it did. Let's see. Yes, 5 iterations. And now look, 3 decimals. So this method is really amazing, right? In terms of what it can do, at least for this 2DOF robot. You see, it's amazing. It's very fast, very accurate. And let me just briefly explain the math behind it, because again, the math of this method is not super complicated, okay? So what you do here is this. When I want to update the location of each joint here, let's say in this first stage, so my P3 goes to P3 prime. So if I have coordinate of P3 and P4 and T, and you know I have all of them, P3 and P4, P4 is my end effector. I have all of the joint locations from what? From my forward kinematics, correct? So I have all of those. So these are all known at any point. Target is also a fixed location. So the question is, how do I find P3 prime? If I can find P3 prime, that's it. That's all I need. Find this location, basically. How do I do that? So for that, I need to first get this unit vector, which connects your P3 to the target point. I need this unit vector of that line. And I choose the direction of it to go from target to P3, like this. And I call this U. Or if you want, you can call it U3 and targets. If I know the location of the target, which I do, and I know this unit vector, which I can easily find by subtracting T and P3, if I multiply that unit vector by this distance D3, that is going to be this vector. And adding that vector to what? To the vector for the target will give me the vector for P3 prime. So as simple as I can say here what? That P3 prime, right? Which you can call it P3 prime X and Y if you want. This is equal to the target point, P of the target, X, P of the target Y, plus D3, the length of that member, times what? Times the unit vector 3t. And the unit vector 3t, as you know, it is what? It is P of 3x minus P of tx and P of 3y minus P of ty. This vector divided by, of course, what? The magnitude of it. Correct? And you know, again, you have the location of T, you have the location of P3. So calculating this should not be any hard thing. Okay. So as you can clearly see, the math of this method is even easier than the math of this CCD method. It's not any hard math, and that's what I really like about this algorithm. It is easy to implement, and you clearly see in terms of the power of the method, clearly outperforms CCD, no doubt about it. Okay, let's see if I can get this guy to go here. There we go, and maybe I can get one more of that. Take it there and then change X to Y. Should be easier. Good. As simple as that. You can get each joint to update its coordinate. You go to the next joint, you go to the next joint, you go to the next joint. This is for forward stage. Now in the backward stage, instead of connecting your points from the last one to the first one to the target, right? So if you see here, I'm connecting each one of my, I connect my last one to the target. Now for the next one, let's talk about that. For the next joint P2, I'm not going to connect it to target. I'm going to connect it to what? To joint 3'. So for the next one, the update equation is different. It's only for the end effector one. This is only for the joint right before the end effector. You connect it to the next joint of it, which is the end effector or UT. But for the next one, your update equation is going to be what? Is going to be a little bit different. So that's your last joint. Now, as I said, for the next joint, where you go to point 2 instead of 3, you have to do a little bit of change. And we can do that. So now your point is going to be P2 prime. It comes from the original P2, whatever it is, right? Well, wait. P2 is going to be the end of it, which is P3 prime. So this is going to be 3 prime, not 2. The new location of joint 3, which is 3 prime, you connect it to 2, and then you update it and call it P2 prime. Correct? And then this D is going to be D2, and this U is going to be U of 2, 3, which is going to be going from 3 prime to 2. So it is going to be 2 here, and it is going to be 3 prime. And then you repeat that. Next time it is going to be what? P1 prime. This is going to be P2 prime. This is going to be D1. This is going to be U1, 2. So it has P1 in it and P2 prime that you got from this stage, right? So you see the number that you get from for P3 prime, you need it here. And you need it in those guys over there. And as I said, when you go to the next stage for P1 prime, you need this P2 prime X and Y, correct? And then you repeat that. So it is in stages. The data you get from each iteration, you need it in each calculation, you need it in the next calculation. So you go all the way like this until your forward stage is done. Now, when you go backward the stage, what happens is for the first joint that is right next to the base, you put this P1 double prime to be the same as original, as I said, location of P, which maybe you can call it, for example, 0, 0, or whatever you want to call it. And then, again, updates, right? So this time your unit vector is going to be like this. This is going to be your unit vector. It goes from the base to the new point, then it goes from the point that is updated to the next one. So it's going to go from P2 double prime to P3 prime and so on and so forth. Okay, so the update formulas are very, very Similar, except that in one stage you start with the target, in the next stage you start with the base, the very pin at the base, and you move forward and you keep updating the equations, the locations of the joints. That's all that we really need, okay? So hopefully this FABRIK method was useful to you, the math behind it, the demo, MATLAB demo for it. Let me show you one more demo before we close this video. So let's put it here. You see, very, very fast with a tight tolerance. Error is 0.1% in 2 iterations. You get the locations to match up to 3 decimals in terms of centimeters, not even meters. Okay, so it is a very, very good, and these are the solutions for theta 1 and theta 2. This method you can apply to a big range of robots. Okay, so hopefully the video was useful to you, and I will see you in my next lecture. Thank you.